There's an insulation panel that gets made without a factory, a furnace, or a drop of oil. You mix farm waste with mushroom spawn, pack it into a mold, and leave it alone in the dark. 6 days later, you take out a solid, rigid board in the exact shape of the mold. It carries the same Class A fire rating as the gypsum board in your walls, with no chemical flame retardants added. It absorbs sound better than cork. And rather than costing carbon to produce, it pulls carbon out of the air while it grows. Last year in Nairobi, a team built a 160 square foot home out of these panels for $208 in materials. So what is this stuff? How does a fungus end up beating plastic foam on fire safety? And if it's this good, why isn't it in your walls already? Let's find out. Stand outside your house on a hot afternoon and listen for the compressor on your air conditioner. It kicks on, runs, shuts off, and some minutes later it runs again. The length of that gap is set almost entirely by the walls around you. That gap is what insulation is really for. Not blocking heat as an abstract thing, but slowing the swing enough that the room holds its own temperature and the machine stays off longer. Space, heating, and cooling account for roughly 48% of all the energy a typical American home uses. So, how often that compressor cycles is most of your bill. And there's a second job that rarely makes the packaging. The same tangle of fibers and trapped air that slows heat also absorbs sound, so a well-insulated wall buffers the road outside and the television in the next room. You feel that one every day, even in a month where the heating never comes on. How well a material does the first job comes down to its R value, a rating of how hard it resists heat pushing through solid material. Higher is better, and it's the number stamped on every bat and board in the aisle. But R value describes the material, not the wall it ends up in, and that distinction is where most homes quietly lose. Picture a standard cavity stuffed with fiberglass bats. The pink stuff fills the space between the studs, while the studs themselves, the wood or steel framing, run straight through from the cold outside to the warm inside. Wood and steel move heat far better than fiberglass does, so every one of those studs becomes a private bypass around the insulation you paid for. Engineers call it thermal bridging, and it knocks 20 to 50% off the effective resistance of a framed wall. Air is the next leak. Fiberglass is spun glass with gaps everywhere, so it does nothing to stop moving air. And in a poorly sealed house, that leakage alone accounts for 20 to 40% of the heating and cooling load. Then there's water, because the moment a bat gets damp, it sags. The air pockets that do the insulating collapse, and it can shed half its R value while it grows mold in the dark. So the conventional stuff carries 3 weaknesses into every wall it goes into. The studs bridge it, the air slips past it, and water wrecks it. What follows removes all 3, and it isn't manufactured at all. Mycelium is the root system of a mushroom. Not the cap you'd put on a pizza, but the dense, thread-like web that spreads underground to feed it. Up close, that web is built from microscopic tubular filaments called hyphae, each one finer than a strand of hair, branching out through whatever it's feeding on. And as those filaments grow, they bind that material together into something solid. That binding is the entire trick. To make a panel, you start with loose agricultural waste, so hemp husks, wheat straw, sawdust, or rice hulls. The leftovers a farm would otherwise burn or dump. You pasteurize it with heat to kill off competing molds. Then mix in grain that's already been colonized by a chosen fungus, usually a white rot species like reishi or oyster mushroom. Then you pack it into a mold and walk away. Over the next several days, the fungus does the manufacturing for you. The hyphae thread out through the loose substrate, digesting it and lacing through every particle until the whole pile has been knitted into one continuous rigid block in the exact shape of the mold. There's no glue, because the fungus is the glue. A white rot species naturally breaks down the tough lignin in plant matter and converts it into a kind of biological adhesive, weaving a 3-dimensional web through the substrate the way roots weave through soil. Once it's fully grown, you bake the panel. Heating it to somewhere between 140 and 158 degrees Fahrenheit kills the fungus, drives out the water, and locks it permanently into shape. What comes out is inert, lightweight, and rigid, a board that was farmed rather than built. The idea isn't new, though it took a while to find a use. A Japanese researcher named Shigeru Yamanaka first tested fungal mycelium as a self-assembling binder in the early 1990s, and the artist Phil Ross built the first grown fungal blocks a decade later. It became a product in 2007, when 2 engineering students at Rensselaer, Eben Bayer, and Gavin McIntyre patented a grown-in-place insulation board they called Greensolate. Now, go back to those 3 weak points, because the way it grows deals with each one. The panel forms as a single continuous piece, so there are no seams for air to slip through. And in the most advanced version, builders pack the living substrate straight into the cavity between 2 sheets of structural sheathing and let the fungus grow in place, bonding directly to the wood on both faces. That creates a solid sandwich panel with no internal studs at all, which means no thermal bridges, because there's nothing conductive running through it to bridge. When a mycelium composite meets flame, it doesn't melt or flash over the way plastic foam does. It forms a layer of blackened char across its surface, and that char acts as a shield, choking off the oxygen and heat the fire underneath needs to keep spreading. Under sustained high heat, the material can convert close to half its mass into that protective crust, rather than feeding the flame. The reason is built into the chemistry of the fungus. Hyphae walls are reinforced with chitin, the same tough material that forms an insect's shell, and chitin is rich in nitrogen. Nitrogen pushes a material to char instead of combust, so the fire resistance here isn't sprayed on the way it is, with the brominated and halogenated retardants soaked into conventional foams. It comes from what the material is made of. Under ASTME 84, the American surface burning test that building codes actually reference, mycelium composites have scored a flame spread index of 20. That puts them in Class A, the top rating, sitting alongside the gypsum wallboard already lining your house at 10 to 15. Researchers have pushed it further still. In one study at George Mason University, a fungal composite was fed sodium silicate as it grew, which raised its ignition temperature from 473 degrees Fahrenheit to 601 and cut the height of the flame it produced by more than half. That test used a different fungal species than the ones grown for insulation panels, so treat it as the direction the material is heading rather than the number off a shelf product. Compare any of that to polystyrene foam, which doesn't simply burn. It melts, drips, and throws off thick toxic smoke while it does. It won't burn, and it won't leak. But this is the part the marketing tends to skip, so here are the numbers straight. On raw insulating power, mycelium is good rather than exceptional. It lands at roughly R3 to R4 per inch, which puts it in the same band as fiberglass and blown cellulose, so it's a fair swap for what's in most walls today. But it does not beat the foams. Extruded polystyrene runs about R5 per inch, and closed-cell spray foam reaches R5.6 to R8. And there's a physical reason for the gap. Those plastics trap low-conductivity gases inside sealed cells, while mycelium relies on ordinary pockets of still air caught between its fibers. To hit the same total resistance, a mycelium wall has to be thicker. But if R value per inch were the whole story, the foams would win, and we'd stop there. It isn't, for 2 reasons that never show up on a spec sheet. The first is that the foam advantage shrinks with age. Those trapped gases slowly diffuse out of the plastic and get replaced by ordinary air, so a foam board's rating quietly falls over the years it sits in your wall. Mycelium has no gas to lose, so its number stays flat for the life of the building, provided it stays dry. The second is everything we've already talked about. A foam-rated R5 in a lab still gets bridged by the studs around it and leaked through at the seams, while a grown-in-place panel with no studs and no seams keeps far more of its rated performance once it's actually installed. On paper, mycelium loses to foam, and in a real wall it claws most of that back. Meanwhile, it's doing things neither foam can do at all. Panels grown from wheat straw have absorbed 87 to 99% of sound at 1,000 Hz, right in the range of a human voice, which beats cork and commercial acoustic tile. And the carbon runs the other way. Producing it emits 0.37 pounds of carbon dioxide per pound of material, about 45% less than petroleum-based insulation. And because the fungus takes carbon out of the air while it grows, the finished panel works closer to a carbon sink than a carbon cost. The British firm Biome has measured its own production line, sequestering 17.5 tons of carbon a month. As for what that does to a bill, one building energy simulation swapped petrochemical foam for mycelium in an identical house and cut monthly heating energy from 435 kilowatt hours to 301, worth about $17 a month. A separate model of a retrofit in Cairo found a 16% cut in total HVAC consumption against an uninsulated wall. Every material has a failure mode, and this one is simple. Mycelium is organic and fibrous, so left unprotected, it behaves like a sponge. Expose a bare panel to standing water or to air that sits above 90% humidity, and capillary action pulls moisture deep into its pores. Water displaces the still air doing the insulating, and since water carries heat far better than air, a soaked panel can shed up to half its R value, the same collapse that ruins wet fiberglass. Worse, if the panel wasn't fully dried during manufacturing, that moisture can wake the dormant fungus back up, and the material can start to decay, smell, or sprout mushrooms inside the wall. The organic substrate is also food for termites and wood-boring beetles, which is why manufacturers mix in mineral additives like borate salts during hydration. But this is a known problem with a known fix, and the fix is design rather than chemistry. You keep bulk water away from it in the first place. So in an exterior wall, the panel sits behind cladding with a 3/4-inch ventilated air gap and a continuous water-resistive barrier in front of it, letting vapor escape while liquid water never reaches the panel. Kept dry, it needs zero maintenance and holds its performance indefinitely, on the same terms as the wood framing around it. If it's fireproof, quiet, and carbon negative, the obvious question is why your local hardware store doesn't stock it, and the answer has almost nothing to do with the material. The hardwall is certification. Before an American building official signs off on any insulation, it generally has to clear ICCES evaluation, a battery of standardized tests for fire, thermal resistance, and long-term durability. That process is expensive, and it was built around materials that leave a factory identical every time. Mycelium is grown, so its properties shift slightly with the strain, the substrate, and the conditions in the room, which makes pinning down the repeatable numbers the code demands slow and capital-intensive. Grown Bio, one of the European pioneers of mycelium building panels, made functional insulation and then left the building sector entirely for packaging, driven directly by the cost of clearing those certifications. Underneath that sits plain economics. Fiberglass is one of the most ruthlessly mass-produced products on Earth, retailing between 30 cents and $1.50 a square foot installed, while mycelium board runs around 66 cents a board foot before you find anyone trained to fit it. And the industry has a structural reason not to care. The developer picking the insulation pays for it up front, but never sees the utility bill, so the cheapest option that passes code takes the job. It's an entrenched, low-margin supply chain, and a newcomer has to climb out of it before price ever becomes the argument. So where does that leave you? This is an emerging material rather than a roll you grab this weekend, and because it has to stay dry, it suits interior, non-load-bearing work best, meaning partition walls, acoustic panels, and anywhere protected from bulk water. It is also not structural, and that limit is worth taking seriously. Ecovative's highest strength product reaches 50 pounds per square inch of compressive strength, but needs a density of 12 pounds per cubic foot to get there, against 60 pounds per square inch, at 2.2 pounds for high-strength XPS. It won't hold up a roof, and using it as though it will is how you end up with a wall that slowly settles under its own load. If you want the real thing today, the accessible entry point is acoustic and interior panels from the handful of companies growing them commercially, with bulk-grown insulation running around $8 per cubic foot. Nairobi's Mycotile is the clearest proof of where that leads, producing 32,000 square feet of sheathing panels a month and putting up that $208 micro home from them. And if you're the experimental type, you can grow it yourself. Pasteurize shredded agricultural waste at 170 degrees Fahrenheit for 20 minutes. Let it cool below 90. Mix 4 parts substrate to 1 part oyster or reishi grain spawn, pack it into a mold, and hold it dark at 71 to 77 degrees for 4 to 6 days. Then comes the one rule that matters more than the rest, and it's the one beginners get wrong. Dry it completely. The panel has to reach 140 degrees Fahrenheit all the way through its core, until its weight falls to roughly 35% of what it was going in. Stop short of that, and the fungus isn't dead, only sleeping, waiting on the first damp spell to wake up and start eating the wall from the inside. Mycelium insulation is still early, boxed out of the wall cavity by certification costs and a supply chain built for pink fiberglass, but it's moving into more buildings every year, from acoustic panels to whole grown-in-place wall systems. If you got something out of this, a like and a subscribe help more of these find their way to people. And if the idea of growing a building material appeals to you, take a look at our video on earthships next. Homes built out of packed earth, old tires, and empty cans that heat themselves, cool themselves, and grow food year-round without ever touching the grid.